Hi, my name is Dale Maley. Today I'd like to tell you about a very interesting project I recently finished, and it's how to design and build a Leibniz mechanical calculator using peg gears. Some background on this project: I have designed and built over 50 wooden hand-cranked toys, including many marble models. Many of these use various types of wood gears. Then I often create YouTube videos showing these projects. A Mr. Cliff Landesman contacted me. He has been studying Leibniz, the German guy, and his mechanical calculator that he made back in the 1600s. Mr. Landesman had developed the idea of using wooden peg gears as a modified form of Leibniz's mechanical calculator. And he also built a prototype of his peg gear idea, and he shared images of that with me. And he had seen some of my YouTube videos where I made various hand-cranked wood models. He asked me if I could build a working model of the calculator based upon his peg gear idea. I vaguely remember hearing about Mr. Leibniz roughly 50 years ago when I was taking calculus at the University of Illinois to get my Bachelor of Science in Agricultural Engineering. I knew he had something to do with calculus, but I'd never heard of him inventing a mechanical calculator. So I had to do a little research about his mechanical calculator. There is a nice animated illustration in Wikipedia that shows you the rough concept that Leibniz had for his mechanical calculator. So, for example, you slide the red gear at the bottom to what number you want to do, and you choose from 1 through 9. Then you rotate the yellow drum 1 revolution, which turns the red gear proportionally. For example, for 2, you rotate the yellow drum 1 rev, and on the red gear it gives you 2/10 of a rev. Then you could slide the red gear to the number 3 position and turn it there. That would give you 3/10 more of a rev, and you add those together and you get 5/10 of a rev on the red gear. Now here's a photograph of Mr. Landesman's prototype, and the peg gears for the main mechanism on the right hand side. He's using peg gears instead of, say, sticks that are on the outside diameter like the Wikipedia example. And then on the left then, he just uses peg gears as the counters. In this case, 2 digits are shown on the left. So when I was in the design phase, in retrospect, I really focused too much on making sure I had enough clearance to move that lower peg gear hub without hitting the pegs on the other wheel. So, to give me more clearance, I initially made the top gear with a 5-inch diameter and the bottom peg gear hub with a 3-inch diameter to give me plenty of clearance. But I forgot that in general, basic mechanical engineering, if you want a 1-to-1 gear ratio, the pitch diameter of both gears must be the same. And I have never done a peg gear with one gear having the pegs radiating out from the outside diameter of a gear. On my past projects, I do what I call gristmill type peg gears, which are different. So for this type of peg gear, the contact point where the pegs hit each other must have the same radius from each of their respective gears in order to give you the 1-to-1 desired gear ratio. So I went ahead and I made up the big hub on top, the blue one. As you can see, is much larger than the bottom peg gear hub. And when I tried it out, just using some vice grips as my crank, I was shocked to discover that I didn't have a 1-to-1 gear ratio on the counters. I had more like a 2-to-1 ratio. And that's when I discovered my error, where I didn't make the 2 gears the same diameter where the pegs contact. Once I discovered my mistake, I went back into my SketchUp free drafting program and did a redesign. So what I'd settled in on was the contact point where the 2 pegs cross over or contact each other. I wanted that 15/16 out from the center. Or 1 and 5/16, sorry. It's kind of hard to read the numbers on this scale, but I want both to be at 1 and 5/16. That gives you a 1-to-1 gear ratio. Now, as you can see, the top blue gear hub is really close to the bottom brown hub. And in retrospect, I should have made that blue hub on top a little bit smaller to give me more clearance between the gears. Doesn't really matter what diameter that blue hub is, because the critical item is the pegs where they contact the mating pegs. So I should have made the blue one a little smaller to give me a little more clearance. But that's how you learn sometimes. So I went ahead and I remade the model, and as you can see, the blue hub on top is quite a bit smaller and actually looks around the same diameter as the bottom gear does. I put the coffee cup on the left hand side because people always want me to do that so they can understand the scale of my models. So let's look at the design features that are built into my version of Leibniz's calculator. So on the blue drum on top, there's 9 vertical rows of 1/4-inch pegs on that blue drum. And then there's different numbers of pegs in each row, so 1 through 9. Down at the bottom down there, that yellow piece, I put a scale on there 1 through 9 to help tell the user where to slide the peg gear hub to. And then on the crank there, you want to make sure you stop at exactly the same point every time. So to do that, I developed a spring detent mechanism, which is a piece of ash, which is very flexible. So you push that spring in, you do one turn clockwise, and then when you come up, it stops when it hits that piece of ash, which makes it stop at the right position. Then down the bottom gear, the peg gear hub, that's the one you slide to the number that you want. Now let's kind of examine the 2 counter wheels on the left hand side of the model. Those have 10 pegs each and they're 1/4-inch dowels diameter. And then the orange gear down the bottom center, or not the gear but the orange peg, that's the one that trips the mechanism when you go over 10. And then these are what I call typical grist mill type peg gears. And I actually use a free online calculator to design those. And if you're interested in making those type of grist mill gears, I encourage you to watch my other YouTube video, which explains how to use the online calculator and how to make grist mill type gears. Now let's watch a couple of short videos which show you how to operate this calculator. Shows the index wheels, how they work up close, and it also I have a video on how to reset the calculator for each math problem you want to solve. So let's demonstrate how this calculator works. Down here, this is a sliding hub, and you set that on the first number that you want to add to. So we'll move it over to say 2. Okay? Then we'll give it 1 crank on the rev, and the counter on the right here will come up to 2. Finish the revolution here. Take it over, let's say 2 plus 3. So we set the slider on 3. We give it 1 crank, and miraculously it comes up to the number 5 on this counter. Now let's say that we wanted to add 5 onto 5 there. Okay, we crank it again, and it comes up to 10. The little orange one tripped the left-hand digit, rolling it over from 0 to 1, so it's 1, 0, or 10. So right now the machine has 10 entered into it, and the slider is set at 5. So in this view, hopefully you can see the counter wheels up here. Right now they're at 1, 0, or 10. Now we're going to give it another increment of 5, which would be 15 on most days. We'll give it another 5 again. Comes up to 20, 25, and 30. Works pretty good. Now that we've finished that demonstration, let's say we're ready for another addition problem and we want to start over from 0. So we need to move the counter wheels back to 0. So that's pretty easy. Just turn here until you see the numbers show up. 0 here. Move this one here until we see 0. Now for some closing thoughts on this project. Looking back, it was kind of a fun project. I like doing new and different things. But the 2 peg gears that create the motion here are very touchy. And as far as I know, peg gears are not really known to be used for intermittent motion and precise angular rotation. For example, in grist mills, they're used for power transmission, and they're generally in continuous contact, and precise angular motion is not very important. Looking back, I probably should have made that top blue hub a little bit smaller outside diameter to give me more clearance between the gears, and yet keep the peg such the contact radius is the same. I don't know a lot about these calculators. I don't know if he had used a different concept like a hub with sticks of various lengths on the OD with a modified mating spur gear would be a better idea or not. Here's a couple concept drawings for that alternate idea of using a drum with, say, sticks glued on the outside diameter. The teeth mating are shown in the upper left portion of that. You have to give clearance when the teeth exit between gears, which I've done. And then if you looked on the lower right, you can see the red sticks. They would be 9876 with different lengths, and then they would mate up with the lower gear, or to the gear to the left, and it would be whatever, say an inch wide, as shown here. So I don't really know if this will be a better or worse idea. You probably have to build it to actually see if it's any more accurate. So in summary, this video explains how to make a modified version of Leibniz's mechanical calculator from way back in the 1600s using simple peg gears. I hope this video gives you some ideas and helps you on your projects. I hope you enjoyed the video, and please subscribe. Thank you.